Everywhere you look, there's colour, and it's celebrated all over the world. Colour is an unavoidable experience. You'll see blue skies, red phones, purple hair. But what actually is colour? The answer to this question became clearer in 1672 when Sir Isaac Newton, the same man who brought us gravity, discovered that white light could be split into what he named the colour spectrum. What Sir Isaac observed was that when white light is directed through a glass prism, the material in the prism splits the light into colours. When Sir Isaac published his findings, many people suggested that the prisms were adding the colour to the white light, so Sir Isaac designed an experiment to prove his observations. In what he called his crucial experiment, Sir Isaac shone light through one prism, producing the colour spectrum, and then directed this coloured light through another prism. If the prisms were adding the colours to the light, then two prisms should result in more vibrant colours. But what actually happened was that the colours recombined into white light, which proved that the colours were a property of the light itself. Here you can see that combining all the colours can, surprisingly, make white. What Sir Isaac had observed was the refraction of light. Colours are observed when white light is refracted because the light contains all these different colours, and each colour leaves the prism at a different angle. The second prism refracts the colours back together into white. So Isaac decided that there were 7 colours in the rainbow that composed white light, despite only observing 6, due to popular belief that 7 was a mystical number. He named the colours he saw and arranged them into the world's first colour wheel. This has been thoroughly useful to artists and scientists alike to understand the scientific and emotional properties of colour. Interestingly, Sir Isaac noticed there are harmonies between the colours, just like there are harmonies in musical chords, so he associated each colour with a musical note. The harmonies between colours are how we came to assign primary and secondary colours, which you might have come across in art. The reason that different colours of light leave the prism at different angles is because light is a wave, and also a particle. The visible colours that our eyes perceive make up one small chunk of the electromagnetic spectrum, as light is a type of electromagnetic radiation. Other types of electromagnetic radiation include X-rays and microwaves. Different types of electromagnetic radiation have different amounts of energy, which is related to a property called the wavelength. The wavelength is the distance it takes to cover one cycle of a wave. Wavelengths of light are usually measured in nanometers, where 1 nanometer is 0.00000000001 meters, so they're tiny. The equation shown here indicates that energy increases as the wavelength of light decreases. One way to think about this is with a rope. If you put a lot of energy into the rope by jiggling one end really fast, you'll get waves of rope that are close together with a short wavelength. If you give the rope less energy with fewer jiggles, you'll get a longer wavelength. You may have heard the term blue hot before to describe something that's particularly hot. This is because blue is emitted by the hottest things, the ones with the most energy. Thus, it can be determined that blue light has the most energy and therefore the shortest wavelength. Red light has the longest wavelength and therefore the least energy. The visible region of the electromagnetic spectrum, the range of wavelengths that our eyes can perceive, fits between around 400 to 700 nanometers depending on the person. The different wavelengths of colours is what determines how they are refracted by the prism. You've probably heard that the speed of light is constant, but light moves overall slower through the glass in the prism because it interacts with electrons in the atoms in its path, so it cannot travel the shortest distance through the glass. When the light wave enters the prism on an angle, the bottom part of the wave is slowed before the top part, which results in a bending of its path, just like when you row one oar on one side of a canoe much faster than on the other to make it turn. Longer wavelengths are less affected, so red light is bent less than blue light, which results in a separation of the colours. So either colour wheel is used to determine what colours or what wavelengths of light an object is absorbing and what it's reflecting. If an object appears blue, that's because it's reflecting blue wavelengths into our eyes and absorbing all the others. If an object absorbs only green light, then it's reflecting all the others, and the colour your eyes perceive is the colour opposite to it on the colour wheel. It's complementary colour. So an object absorbing only green light will appear red. So now you know what this colour phenomenon is, you may be wondering what all that information is used for. Well, colour theory has been applied in some really interesting ways and has deepened our understanding of many natural occurrences. Why the sky is blue remained a mystery for a long time, and it was the knowledge of the various wavelengths of colours that led to the realisation. It turns out that the small particles in the air interact more with smaller wavelengths of light, so they're more effective at scattering the blue wavelengths of light. The result is that blue is scattered into your eyes, while other colours are directed more towards the ground. The appearance of a rainbow is due to the refraction of light by water molecules in the air. This is why you'll only see a rainbow during or after rainfall. The main information that astronomers have to analyse is the light that comes from stars. One of the fundamentals to such analysis is to determine the colour of the light that comes from the stars, as it is an indication of the size and temperature of the star. This plot, called the Hertzsprung-Russell diagram, is used to classify stars based on the brightness and colour of the light that they emit, and can also be applied to find out how far away the star is. Scientists have learned a lot about the structure of atoms, and one observation is that atoms absorb and emit light with very specific energy levels, which we now know means specific wavelengths or colours. This means that elements can be determined based on their interaction with light. Spectrums have been developed for each element and can be used, for example, to determine what elements are present in a planet's atmosphere. Scientists have also discovered that the intensity of the colour depends on how much of the element is present. How much of something you have in a solution is called its concentration. There are many instances, such as in water analysis, where it's important to know how much of a substance is present, and by measuring the absorbance of the solution, the concentration can be determined. This analysis uses a technique called spectroscopy. Plants harness the energy of sunlight. Sunlight contains all the wavelengths of light, however not all the wavelengths are absorbed by the plant. Most plants appear green, which means they're reflecting green wavelengths of light. This means they must be absorbing the complementary colours red and blue. Colour is an amazing part of our world and has led to many fabulous discoveries, and will surely lead to many more.